grade 11 mindsetters, welcome to today's physical sciences show. Today we have a special revision lesson on Newton's laws. We have selected highlights of lessons shown earlier in the term to help you revise term 1's work. Please post all your questions and comments on our Facebook page on facebook.com/learnextra or on Twitter @learnextra so we can help you with your revision. Don't forget to download today's show notes on learn.mindset.co.za or click on the link on our Facebook page. Now it's time to get on with our lesson.
What's the relationship between forces and motion? Before we get there, to really understand this, we need to get the terminology right. This is quick revision of grade 10 work, so you should know this, and it's work that we've done. We always talk about motion as a change in position. The other word for that is displacement. The symbol for displacement is either delta x when it's horizontal or delta y. And when we're calculating change in position, we take the final position minus the initial position and we work out the difference. Remember that change in position is a vector, and vectors mean that direction matters. So you've got to be very clear. What's the positive direction? What's the negative direction? Make sure you take note of that. Then velocity. Velocity, it has a symbol V, and we say that velocity is a vector. Yes, it's a vector, and it's equal to the change in position over the change in time. So a short way of saying that, it's the rate of change of position. Vector, because it only deals with the final position minus the initial position divided by the time. So if we had to run around an athletics track and the start position and the end position were exactly the same, then our velocity would be 0 because the change in position is 0. Please make sure that you've got that. It's different to distance. It's different to speed. Make sure you understand that speed and distance are scalars, whereas change in position or displacement and velocity are vectors. Now, this next one. Oh, there was one other thing I wanted to say. There are different types of velocity. Velocity we need to understand. You can get constant velocity, and they sometimes call it uniform motion. Uniform. Uniform, it's all the same. I'm doing the same thing in the same time every time interval. I'm covering the same change in position every time. So uniform motion, constant velocity. There's another word that we talk about is average velocity. And that means that we're going to take the final velocity plus the initial velocity divided by 2. Or we can talk about, very important, instantaneous velocity. Now what do you think that means? Instantaneous? At an instant, at a moment in time, exactly as the clock goes to 10 seconds past. That's the velocity we're wanting. Okay, acceleration is simply the change in velocity over the change in time, or the rate of change of velocity. Now guys, what you've got to grasp here and understand is that in terms of the grade 11 work and in terms of work that we do at school, velocity is acceleration is always constant. You won't get a changing acceleration. Acceleration is always constant. That means it's not going to change. The first thing we want to talk about is what's this law called Newton's law of gravitation all about? Universal law of gravitation. Now, you must have heard the story about Newton sitting under a tree and he suddenly sees an apple falling. Now, how did he explain it? What did he say was happening? Well, there's a whole lot of anecdotal stories about that you can read in lots of different textbooks. But really the story that Newton was doing, looking under the tree, was he was observing the stars. He was observing the moon, and he wanted to understand why they were in a fixed orbit, Why it was that he looked at and he saw the stars always in the same sort of pattern. Yes, they rotated in terms of the time of season, but he was trying to explain what was going on. And then he saw the falling apple at the same time, and he suddenly realized that there was a force between objects that have mass. He recognized the sun has mass, recognized the moon has mass, recognized the earth has mass, the stars have mass, the planets have mass, and because they have mass, there must be this force pulling on them. So that's why he came up with this idea, which we call the law of universal gravitation. So here it goes. We want to break it down and explain it step by step. He said, the force of attraction between two objects in the universe, any two objects, they must have mass. Okay? They must have mass. And what we say is they're directly proportional to the product of their masses and inversely proportional to the square of the distances between their centers. Wow, that's a huge mouthful. I need to take it one step at a time. And I want to explain to you each of those important terms and revise with you. I know you've been dealing with relationships right from probably grade 8 when we started some natural sciences in high school. But let's just draw a picture so we can see. Let's talk about this object as having a mass, m1, this object having a mass, m2. The first statement is the force of attraction between these two is directly proportional to the product of the masses, m1 times m2. Product means multiply. What does directly proportional mean? Think about it for a minute. Hope you've got it. That's right. When you increase 1 by a certain factor, then the dependent variable will increase by the same factor. So let's just take it like this. If we start with mass 1 and then we double the mass of m1, what's the force going to do? Well, it's going to double as well. So if we increase this mass, make it go up by a factor of 2, then the force will increase by a factor of 2. Now, how about this? If we increase the force of the mass of m1 and the mass of m2, so now we've multiplied the one side by 2 times 2, which is 4, then we must multiply the other side by another 2, so it's gone up by a factor of 4. Guys, you've got to be very careful with this. You've got to know it. Directly proportional means if I decrease the 1, halve the mass. So they often say halve the mass. That means I multiply by a half. Then I must multiply by a half on that side. What I do to the one side, I must do to the other. And it's a proportionality factor. It doesn't mean that I can add or subtract. No, it's multiply either by a whole number or multiply by a fraction. Yes, we can divide. We know that's the same as multiply by a fraction. Okay, so there's the directly proportional. There's one other thing that you mustn't forget when we're dealing with directly proportional. And this term is very, very important because we'll come across it in many different places in this year and in grade 12. So you need to know this. If we were to plot a graph, okay, and we plotted a graph of factors that are directly proportional to each other. In this case, I'm going to do the product of the masses, m1 times m2, and I'm going to say force is on that set of axes. Now, in this example, and in fact in any example, the things that go on the horizontal axis, they're known as the independent variables. And this one on the vertical axis is known as the dependent variable. Now, when the things are directly proportional, then we know, and I want to get a nice straight line to represent it, then we know passing through the origin, there will be a straight line. Okay? So it can't be just any old place that it starts from. It's got to go from the origin. So let me make sure that it is at the origin. The origin is this point of 0, 0. So it must go through the point 0, 0. Okay? It's got to go through that point. It's got to start at the origin, and it's a straight line. It has a constant gradient. It's directly proportional. Now, this you should be able to apply to Newton's second law. Remember last week we said the acceleration is directly proportional to the net force. So if you've been plotting graphs for Newton's second law as a practical, then you'll know that you've got directly proportional. This is another example of directly proportional. Okay, let's go on to the next part of the law. So we've covered the first part. We've covered up to there. But it then carries on and says, and inversely proportional to the square of the distances between their centers. Okay, now let's break that down just to make sure that we've got it. When we're talking about Newton's universal law of gravitation, we're talking about masses, and we've illustrated them as spheres, and we say they both have centers. And what we're interested in is the distance from that point, from M1 center to M2 center. So that distance there, all the way through. Now, this would be the radius of M1. This would be the radius of M2. And what we're wanting to get is the whole distance, not just the radius, but just remember that it's from that point all the way to that point, and it's from the centers. We call that distance, let's call it an R. I'll even call it a big R. What we're going to say is that the force is inversely proportional to R squared. So if we're taking that whole distance as R, and we're not just talking about R, but R squared. Now guys, that's quite a factor, that we're having to square R. And this is the place that a lot of people make mistakes. I've even made mistakes here in terms of squaring things. So you've got to make sure that you square the R. You square the distance. We'll see what that means. But guys, it's not directly proportional. That's not true. It's inversely proportional. Now, another way of saying inversely proportional to the square of the distances is to saying it's directly proportional to 1 over R squared. So that's a really important idea that you've got to get clear. That when we say something is inversely proportional also means directly proportional to 1 over. Directly to 1 over. So if it's inversely proportional, so F is inversely proportional to R squared, then it's directly proportional, then F is directly proportional to 1 over R squared. Please get that right. So when we go back and look at Newton's second law, we would say the acceleration is inversely proportional to mass. We can say A, the proportional sign, this sign, which is saying proportionality. There, as the one goes up, the other goes up. Here we're saying as the one goes up, the other goes down by the same proportion, but the same proportion squared. So it's not, that's why this inverse proportionality is sometimes difficult. And we're going to spend a little bit of time talking about that in some of the problems. Now, you're going to say to me, but guys, I don't want to deal with these proportional signs all over the place. I want to have an equal sign. And so in physics, when we have proportional signs, we can change them to equal signs if we introduce a constant. So we can now say the formula looks like this. Here's the constant, which has been found through measurement, G, M1, M2 over R squared.
Alright, Mindsetters, I hope you guys are enjoying this revision session. Remember, if you are struggling and need help, please post your question on our Facebook page or send an email to helpdesk@learnextra.co.za. Now it's time to take a quick break, so don't go anywhere. We'll be right back. Welcome back, guys. I'm sure you've seen and heard about the Mindset Rack nomination and hope you'll get involved. If you make a video, post it on YouTube with the title #LearnExtraRack followed by your name or the name of your group. If you don't have a video, post a photo on our Facebook page and tell us what you've done. Let's use this short holiday to make a big difference in other people's lives. Now, let's get back to revision.
Guys, we've had a bit of a summary of this relationship between force and acceleration and motion. Now let's get into the questions. Make sure you've got your notes. And guys, get your notes early so you can try these problems so that when we're going through them, you are comfortable, you can check your answers. Okay, let's get to those notes right away. So the first question that we've got says, a box with a mass of 60 kilograms is pulled along a rough floor, important, by a boy exerting a force of 120 newtons. So there's a little diagram they're giving, making it easy. So there's the force applied. I'm just going to call it force applied, APP. And there we've got the mass of the box, which is 60 kilograms. But we were told that there's a rough floor. As soon as I see that word rough floor, or rough surface, or even through mud, or over a carpet, or over stone, then I must be thinking that there's a frictional force involved. Okay? I cannot not think of friction unless it specifically says on a frictionless surface. Okay? So on this diagram for myself, I'm going to say that I will draw in a frictionless surface. Now notice a frictional force, and I'm saying it's acting in the opposite direction to the applied force. The applied force is to the right. The frictional force always opposes motion. Now let's have a look and see what the question's actually asking us to do. I was just interpreting the information there. It says draw a force diagram to show all the forces acting on the box and label the forces. Now guys, in this question, we've got to be really careful because we've got to apply all of Newton's laws, not just Newton's second law. So I'm going to draw the force diagram underneath here, and we're going to come to it. I'm going to draw the box as a dot, almost like a free body diagram. And the first force that I know is definitely exerting is the force of the boy, the applied force. And we're going to say that that's 120 newtons. Then the other force that I know that's definitely exerted is the force due to gravity. And this is Fg, which is equal to the mass of the box times the acceleration due to gravity, mg. And we can work it out. It's 60 kilograms times 9,8. And if we use our calculator over here, just move it to that side, we get 60. Turn that ink off for a minute, and we get 60. It needs to go. 60, there we go. Let's do it again. 60 multiplied by 9.8 equals 588. So 588 is my answer that I'm looking for, 588, and that's newtons. Now, there is another important force. If the force downwards is 588, then we know that on the Earth, very important to notice this, the box will be pulling the Earth upwards at 588. Those would be the pair of forces that we call the action and reaction pair, or we call them the pair of forces from Newton's third law. But from our discussion on friction, we know that there is another force that is acting on this box, and we call it the normal force. Now, in this case, the normal force is the force of the surface acting on the box, and what we do know is that the normal force is the same magnitude as the force downwards. It is not a Newton 3 pair. It's not a Newton 3 pair. Please take note of that. The box pushes down on the surface, and the surface pushes up on the box. the Earth pulls down on the box, and the box pulls up on the, those are the pairs. Make sure you've got the bodies correct. We'll revise, if we've got some time, Newton's third law at the end. And the last little force that we want to consider is the force of friction. And we don't know what that is. And we'll just call it the frictional force. The reason we know it's there because it said it was a rough surface. The frictional force. Okay. So guys, there's our force diagram. It's showing all the forces and we've labeled them. We must understand what these forces are. We must be able to apply, interpret exactly what's going on. So I'm just going to make sure that we understand that that force and that force are equal to each other. So really, when we're talking about this object moving and across the surface, we're only interested in those. So when we asked the next question, which was to calculate the magnitude of the frictional force caused by the floor if the acceleration of the box is 1,5 meters per second, then the only forces that we're going to be looking at are the ones that are in the horizontal. We're going to separate it and say we're wanting to look at the horizontal forces. And if we've got a frictional force to the one side and an applied force to the other side, what's the overall result? Well, we call that the resultant or the F net. The resultant or F net. And Newton's second law tells us that because the acceleration is directly proportional to the force, we can write the resultant or the F net is equal to the mass times the acceleration. Now, guys, I want you to understand that F net is not some introductory fairy force that comes in from the aliens. Okay? It is not an imaginary force. It is this force here, this one, plus that one. If we add those two together, then we're going to get F net. So on my diagram, what I'm going to do is I'm going to say the direction to the right is positive. And I'm going to apply that sign convention. And I'm going to say, let me find out what the horizontal forces are. They are the force of friction plus the force applied. And I'm going to say that's equal to the mass times the acceleration. But remember that to the right is positive. So if we look at this, what we're going to recognize is that from Newton's second law, the acceleration is in the direction of the net force. We recognize that the applied force, in this case, the applied force will always be bigger than the frictional force. So the acceleration is also in that direction. So the acceleration is positive. The only thing that is going to be negative is the frictional force. So we're going to say we expect the frictional force to be a negative, less than 0. Now let's substitute some values in and let's see how we go. And we're going to say we don't know what frictional force is. We know what the applied force, it was a positive 120. We know what the mass is, it's 60. We know the acceleration is positive. Mass doesn't have direction, it's a scalar. 1,5, let me just redo that. 1,5 meters per second per second. We multiply that together and we'll get this is 90. Now I want F of friction on its own. So what am I going to do? I'm going to subtract the 120. So I'm going to subtract that from both sides and I get minus 120. And the end result is that I can say the force of friction is negative 30 newtons. Can I leave it there? Guys, no. You must never leave an answer with a negative sign in front of it or a positive sign. You can't leave a vector without describing the direction. So we must interpret this. We must say, therefore we can say the frictional force is 30 newtons in the opposite direction to the applied force. The reason I didn't say left and right was because they didn't tell me in the diagram that it was to the left or right. They drew the diagram, yes, and I might be okay, but not every time. So what we need to say, it's in the opposite direction to the motion, or the opposite direction to the applied force, or the opposite direction to the acceleration. Please be very specific. If they tell you that it's traveling north, then you know that the direction of the force will be to the south, and so on. Okay, Abby, we're going on to the next question. So let's have a look at it. This one is a little bit tougher, and it's a typical exam type question. So I want you to pay very careful attention. Don't get lost and don't get hung up and say, I don't want to do this. No, you guys, you can manage this. This is not that difficult. And after you've done a couple, you'll understand that you can do them. So it's all about confidence, and it's all about making sure that we've got it right. So let's read it. Let's make sure we've got it right. A force of 10 newtons is used to pull dynamics trolley A along a frictional horizontal force. The trolley A is attached by a light, non-elastic string to trolley B. So there we go. Trolley A has a mass of 1 kilogram and trolley B has a mass of 500 grams. The first thing they're going to ask us is to calculate the acceleration of trolley A. So let's just make sure that we've got our detail correct. That's A and that's B. And we want to calculate the acceleration of trolley A. Then they ask for the tension in the string that joins trolley A to trolley B. So they want this tension. Now, something interesting about tension is that the tension in a string will be the same at either end. Okay? What we've got to do with this sort of problem, we've got two objects. So we've first of all got to decide our direction, and then we've got to draw some diagrams. So I'm going to start right there. And I'm going to start by saying, let's have a look at trolley A. And I'm not a very good artist, so I'm going to call that A. And I'm going to say, what are the forces on trolley A? And trolley A has a force exerted, which was the applied force, which was equal to 10 newtons. It then had another force, the force of the tension of the string pulling on it like that. If I now look at trolley B, and I want to change the color of my pen, and I'm going to look at B, assuming that this was a frictionless surface, and we're not having any friction, we're going to say that the force on B was only to the right, and it was the force of tension. So let me just correct that. It's the force of tension applied in the opposite direction. Now remember that what we've now got to look at is what's the net force? What's the expression for net force? We can say the net force on A is its mass times its acceleration, and the net force on B is going to be its mass times its acceleration. We can work these one at a time, or we can work them together. I'm now going to, having set them up, I'm going to set up the equations, then I'm going to do the calculations individually. So what is the net force acting on A? Well, I hope you can see if we define to the right as positive, and that means to the left is negative, that we're going to say that it's force plus the force of tension. That's what the net force is. We're adding those vectors as vectors is equal to the mass times the acceleration. And over here, what are the forces on B? This is B, object B. What's the net force on B? Well, it's simply the force of tension. That's equal to its mass times its acceleration. Now, guys, the important thing here is that if A is traveling at a certain acceleration, then B will have the same acceleration. Okay? That's why they linked with the string. You can't have different parts of the same system accelerating differently. They're together. So what I'm going to do now is I'm going to substitute some numbers in here, and I'm going to see if I can resolve these equations and join them together simultaneously. So the only thing that I know is that this is 10, and I know that the force of tension is going to be a negative force. So I'm going to make sure that I understand that that's going to be a subtraction. It's going to be, I'm going to subtract that force of tension from there. Because the force is applied in the positive direction, the force of tension is in the negative direction. Now, we know the mass over here was, let's just check the question. The mass of A is 1 kilogram, and the mass of B is 0.5 kilogram. So this is 1 times A, and this we don't know, but this is the mass times 0.5. This is the acceleration we don't know. The mass is 0.5, and the acceleration is A. Now I'm going to combine those two, and I'm going to do it like this. I'm going to say, write this one up at the top, Ft is equal to A, and I'm going to write the second one, Ft is equal to 0.5 A. Now look at this. This is really interesting. You can do it a different method. This method is by elimination and by adding. If you set up your questions correctly, and you've used your correct signs, then what you'll be able to do is add the two together, and the Ft will cancel out. So when I add this together, I'll get 10. I will get this one being 0 here. So 10 is equal to 1.5 A. Now, to get my answer, what I need to do is I need to therefore say A is equal to 10 divided by 1.5. And if I go to the calculator, just clear it, I'm going to go to 10 divided by 1.5, and I get an answer of 6.67, which is equal to 6.67 meters per second per second. And notice that I need to say, if it said magnitude, no it didn't, it said calculate the acceleration, and I must say in the direction of the applied force, because that's where it was. In the positive direction, in the direction of the applied force. Okay, right. Let's have a look at the last part, because this is really the interesting part. How are we going to find tension? Well, we're halfway there. Not even, we're more than halfway there. We've got acceleration. Notice that we've got two equations. We've got this equation over here, and we've got this equation over here that both have an Ft missing. You can check this by substituting the values in. I'm going to do it very quickly. I'm just going to say, I'm going to use this equation, and I'm going to use the acceleration I was given. I'm going to say, therefore, Ft is equal to 0.5 times the acceleration, which was 6.67, and if I'd used the calculator to do that, just multiply this by 0.5 times 6.67. It's not done it properly. Let's just do this again. Multiply equals, and we get an answer of 3.35. I'm going to round that up to 3.34. So my answer for my tension is 3.34 newtons. In which direction? Well, if it's acting, it depends. It acts, because it's in the rope, it acts on B to the one side and on A to the other.
I'm sure you've seen the walk together photo on our page. Please post a caption and like the captions that you think are best. The 3 captions with the most likes will each win a pair of tummy tackies. We'll post the winners on Friday, so get to liking and get all your friends to like too. Now it's time to take a break, so don't go away. We'll be right back. Welcome back from the break. I know you can't wait for the term to end and for the holidays to start. This year we bring you revision sessions from term 1 from the 28th of March till the 6th of April. These will be repeats of all the Learn Extra live shows from term 1. These programs will run from 9 a.m. in the morning till 7 p.m. at night. Go to our website learn.mindset.co.za for all the details. But for now, let's get back to the revision.
So let's go to the improve your skills questions now. These are in the notes. These are some typical exam type of questions. So I hope you got them, got your notes. Get the notes as soon as you can. Download them from the website. Do them before the show. Get going. Get some work done. Right, let's have a look at what it says. It says to us some important information. It says the radius of the Earth is 6,4 times 10 to the 8 meters, and its mass is 6 times 10 to the 24 kilograms. Then it says use Newton's law of universal gravitation to calculate the acceleration of an object falling from the second floor of a building, and it tells us that we can ignore the effect of air resistance. So we can ignore the frictional effect. Right, guys, what have we been given? We've been given the mass of the Earth. The mass of the Earth we've been given as a big number, 6,4 times 10 to the 24. We've been given the radius of the Earth. So the radius of the Earth, we've been given that is 6,4 times 10. This one wasn't 6,4. This was just 6. Sorry, I made a little error there. So this one was 6,0. This is 6,4 times 10 to the 8 meters. And this was kilograms. Okay? And what we're asked to do is to find the acceleration of an object falling from the second floor of the building. Hey, this seems impossible because I don't know anything about the object. I just know that it's falling down towards the ground. It's second floor of a building, not very high. So we can ignore air friction. What am I going to do? And what it's asking me to do is to calculate the acceleration. Where am I going to get all this stuff? Well, relax. Don't panic. What we've got to do is let's write the formula out. So the first thing that I'm going to do is I've got that information. I'm going to say we know the force of attraction between the object is equal to G times the mass of the object times the mass of the Earth divided by the radius of the Earth squared. That's the equation. Now, what else do we know about the object? We know it experiences a force. What force does it experience? And here's the important thing, guys. We need to get this very clear. It experiences a force, a pull down of the force of gravity on it. As I'm standing here, the Earth is pulling me down. And what force is it exerting? It's exerting a force that we call, another way of saying it, it's the force is equal to the mass times the acceleration due to gravity. And this is sometimes even called my weight. So into this formula which you might have seen when we dealt with Newton's second law, we can now combine these two and we can say, hold on, we know that mass, that the force acting on the object is the mass times the acceleration to gravity. And that's what we wanted to find. We wanted to find the value of little g. And watch here. G m m e over r squared of the Earth. And what do you notice? I hope you can see that the mass of the object cancels out. I can divide both sides by m and they cancel out. What is this telling me? And it's a very important thing you've got to know. That objects accelerate close to the Earth independently of their mass. So if we ignore friction, they have the same acceleration. The only thing that gravitational acceleration depends on is this constant, g, the mass of the Earth and the radius of the Earth. Okay, guys, that's the physics part. We've got to get that clear, and you've got to know it. You've got to make sure that you understand that the attraction between an object and the Earth is known as its weight and as mg. We can then find out what g is by doing the substitution. And this is where it becomes easy. I've just got to go back and remember that value. Megan, can you take a note of this? 6,67 times 10 to the minus 11. 6,67 times 10 to the minus 11. We're going to need it for just now. 6,67 times 10 to the minus 11.
Yeah.
Okay, got that right. The mass of the Earth was 6,0 times 10 to the 24. So I'm going to put that in brackets. 6,0 times 10 to the 24. And then I'm going to take the radius of the Earth, which was 6,4 times 10 to the 8 meters, and I must square it. Now, please watch very carefully that you do square it. You must put it into the calculator. And with this particular equation, you need to be very careful of using your calculator correctly. So make sure you're familiar with scientific notation and exponents. So let's go to our calculator here. We're going to say 6. Let's just take that off for a minute because it's going to give us grief. We go 6,67 exponent negative 11. And we want to times that by 6. Check the reading, times 10 to the 24. And that will give me my numerator divided by, now I'm going to be careful because I know that I've made the mistake before. 6,4 exponent 8, and I've put it in a bracket because I want to square that whole thing, and I'm going to then make sure that that's the denominator, and I'm not forgetting that that's squared. And I push equals, and look at the size of this force. If I go to my scientific notation, which I'm just going to do it to engineering, you can see that it is, divide this, just to take it out of engineering for a minute, or it's going the wrong way. It's getting too big. Let's go back. It's gone too much. So what I'm going to do is I'm going to say that this is 9,7. Let's just make sure that we can go back one step. I want to go back, and it's not letting me. 9,17, and I'll get the reading here. It's going to be 77, 2 decimal places, times 10. Now, let me try and work out what it's given me, because I've made a really silly mistake there. I thought I was getting to the scientific notation, and I'm not. So if I do 12 places, 1, 2, 3, 4, 5, 6, 7, 8, 9, then that's going to be times 10 to the minus 2, I think. Okay, so we'll check it in the break. It's either times 10 to the minus 2 or times 10 to the minus 3. I'm not exactly sure why it's come out like that, because it should have come to a closer number that we're more familiar with. Because if you look at 9,7, that should really be the acceleration due to gravity. Maybe there's a slip, there's a factor of 10. I'll look at the question, but I hope you can see that that is the way to do it. This, of course, needs to have units, meters per second, and we'd get that as an answer. Okay, let's move on to the second question. We're going to use the same sort of idea, and let's see how we manage. So, calculate the magnitude of the force between a person with a mass of 100 kilograms and a person with a mass of 75 kilograms if they are 0,5 meters apart. Now, I know this is corny, but you probably hear it as whenever you doing this section, somebody will come up to you and say, did you know that I feel a force of attraction towards you? And it's nothing to do with your sparkling personality, it's just to do with your mass. We'll apply exactly the same formula. We're going to say, what's the force of attraction when we have G, M1, M2 over R squared? And guys, I'm not even going to go too far with this. I'm going to substitute the values in 6,67 times 10 to the minus 11. Mass of the one person was 100 kilograms. There must be SI units. And the other was 75 kilograms. And now we must make sure that we take 0,5 and we square it. 0,5, not 0,8. 0,5, and we must square it. So let's do that. Let's see if our calculator will behave, and we'll check it out in a minute. 6,67 exponent minus 11 times 100 kilograms. Make sure it does do what I say, times 75. Now, divided by 0,5 squared. Okay? That gives me an answer, and again, it's got 0,00, and I don't like those answers. So, I'm going to count the number of decimal places. 1, 1, 1, 2, 3, 4, 5, 6, 7. And that's, sorry, let me do it again. 1, 2, 3, 4, 5, 6. If I multiply this by 10 to the 6, then I'll get the answer of 2,0 times 10 to the minus 6
For
newtons.
those who don't know how to do scientific notation, is it just moving the comma?
Correct. So let's just check that out. And what I'm going to do is I'm going to multiply the answer by 10 to the 6. So I'm going to say multiply by 1 exponent 6. And let's see what we get as an answer. And there you go. So I've checked it.
Yes.
Okay? Because I've said it was 2 times 10 to the minus 6. If I divide it by 10 to the minus 6, I would get 10 to the negative 6.
Yeah. Just
Okay?
for those who don't know.
So you've got the answer. You know that it's right. If your calculator, make sure your calculator is set up in scientific notation. Read the instruction manual to get that. So guys, in this section, you can see this question, really just plug and play. You're just putting it in. The big thing that I want to make sure of, and to say to you again, you've got to square. You've got to make sure that you square that distance. Recognize that this is a very, very small force. You know, it's a millionth of a Newton. It's not going to be, or 2 millionths of a Newton. Not very big at all. Okay, let's go to the next one, which requires a little bit more thinking, and we're going to have to play with it a little bit and understand the physics. So let's go to that, and let's see exactly where we are. So it tells us now the force between a man with a mass of 100 kilograms and the Earth is 9,800 newtons. If the mass of the Earth is taken as 6 times 10 to the 24, determine the radius of the Earth in kilometers. Now, we're going to check if our answer that we used, the data that we used earlier, is actually accurate. So let's do it. We're going to use exactly the same formula. F is equal to G, M1 for the man, ME for the Earth, divided by R squared. But now, in this case, what are we asking? We're asking for R squared. Don't be tempted to change the formula. You must substitute in first. So we're going to substitute in for all the things that we're given. We're told that the force between the Earth and the man is 9,800. So we're going to put the 9,800 there. We're going to put the 6,67 times 10 to the minus 11 over there. Put it in brackets so we don't forget it. We've got the mass of the man. He's 100 kilograms. And we've got the mass of the Earth is 6,0 times 10 to the 24 kilograms. We don't know what r squared is. So that's what we've got to find. How are we going to do it? Multiply both sides by r squared, and we'll get the following. We'll get r squared, and then divide both sides by 9,800, and 6,67 times 10 to the minus 11 times 100 times 6,0 times 10 to the 24. And there you go. It's a simple matter of putting this into the calculator. Will we have the right answer then? Not quite. What have we got to do? We've got to remember that this is r squared. If I want to get r, what am I going to do? I'm going to take the square root of both sides, and I'm going to say it's the square root of this, 6,67 times 10 to the minus 11, okay, times 100, times 6,0 times 10 to the 24, and that's all in the square root, and then underline it by recognizing that this is the force, which is 990. Guys, I'm not going to do the calculation of that. Think you can manage on the calculator. This is not about calculation. I want you to see the different types of questions they can ask. Let's do one more, because this one gives us a little bit more thinking to do in terms of the actual law. It says, an object has a mass of 48 kilograms. What gravitational force will this object experience if it is released from a height equal to twice the radius above the Earth? And then they give you the data. So, this is a question that came to us on the help desk. Came the other week, and I want you to think about it very carefully, because the easiest way to do this is to draw a diagram. And we say that the object is above the Earth's surface, and it's a distance of twice the radius. So there's one radius, there's another radius, and there's the third radius from the center of the Earth. So the distance that the object is from the center of the Earth is 3r. And that's the critical point that you've got to make. We're told that it has a mass of 48 kilograms. We're told all the rest. And what we're having to do is to work out what gravitational acceleration will it experience. We don't even need to use its mass. We can simply say G is equal to big G, the mass of the Earth, over the radius of the Earth squared. And there we go. We've got the distance, and we've got the thing to substitute. Last thing that I'm just going to do is I'm going to put the values in so you can see that we've got them. 6,67 times 10 to the minus 11 times the mass of the Earth, and I'm going to squash here, 6,0 times 10 to the 27. I think it was 24, wasn't it? Let's just check it. 24 kilograms. 24, there we go. And I'll move it now. And then the radius is 6,4 times 10 to the 8. And I'm just, this is jumping, and I don't know why. 6,4 times 10 to the 8. Don't forget to square. And again, I hope I can leave that for you to solve. But hold on, I've made a mistake. It must be 3 times that, because it's 3 times the radius. So don't forget, don't be in a rush like I was, because I can see time's running out. Make sure that you've got 3 times the radius. Why is it 3? Because it's 2 above the surface and 1 below to the center. Very, very important.
We've come to the end of our show. Thank you so much, Mindsetters, for joining me and for chatting to me during the show. Remember to visit our website, learn.mindset.co.za, to get your notes and to watch the videos from the term. Goodbye.